All right, friends, welcome to the penultimate class of 352. You were almost done. So we're going to learn two new reactions today. We'll get through most of them. We'll probably need some more time next time. And then that will be it, though I may talk a little bit about plastics and polymers next time. So the reaction we're going to start with is weird because it doesn't really, at least at first, involve transition metals, so it doesn't fit very well with the other reactions we've been doing. Nevertheless, the title of the chapter is Carbon-Carbon bond-forming reactions, and so this is one of them. So they just sort of stuff it in here, and it's interesting enough that it's worth talking about. So the reaction will start. And I had a terrible time during the first hour, during the 9 o'clock hour with this Apple Pencil. It's like sometimes drawing nice lines and other times drawing really thin lines, and I don't know what's going on. So I will try to keep my frustration with the Apple Pencil internal so that you don't have to see me melt down. Okay, so the reaction is going to involve an alkene, and let's just use this E or trans alkene. The reagents, oh, see, there it goes. I think it knows when I'm lecturing because I was doodling all over the place before class, and then it just isn't working now. So you're going to use chloroform, which is CHCl3, and then you're going to need a base, tert butoxide. And the product, horror of horrors, is this three-membered ring, and the methyl groups that were trans to each other in the starting material have to be trans to each other in the product. And if you make a molecule that's chiral, because the starting materials were not chiral, you have to make both enantiomers. And interestingly enough, if you switch the stereochemistry of the alkene starting material, but otherwise use the same reagents, you end up with the three-membered ring, but again, the methyl groups have to be where on the ring in the same orientation with respect to each other that they were in the starting material. So the cis alkene leads to cis substituted three-membered ring, and the trans alkene leads to the trans substituted three-membered ring. And this now is another interesting way to test your knowledge of stereochemistry. The compound below is a meso compound. It has stereocenters, but it is nevertheless not chiral because of a plane of symmetry. All right, so what on earth is going on here? Because I thought that chloroform was basically a solvent, and the times you've seen it may just be as an NMR solvent when it's CdCl3. So the mechanism is going to require us to think about a new kind of reagent that we haven't dealt with before. So it may not be surprising that the proton on chloroform is somewhat acidic because of the electron withdrawing effect of those nearby chloro groups. So a strong base like tert butoxide can remove a proton from chloroform, and when it does, that's going to generate this carbon ion, and of course the conjugate acid of tert butoxide, which is tert butanol. So this is CCl3 minus. And what happens now is unexpected. But in order to get rid of the negative charge on carbon, chloro is a good leaving group, so chloro can leave. And what is left behind after chloro leaves is this weird neutral species. The negative charge goes with chloro, and you're left with this neutral molecule that nevertheless only has 2, 4, 6 electrons. So you might expect that to be somewhat reactive because it doesn't have a full octet. And that's true. This is a hypovalent carbon. But the structure of this intermediate is pretty interesting. So we're going to call this a carbene. And that's, I don't necessarily know where the nomenclature came from. A carbene is a neutral carbon that has a lone pair on the carbon. And if we look at the structure of the carbene, it's the C-Cl bonds are all in the same plane. The carbene is roughly sp2 hybridized. The lone pair is held basically in an sp2 type orbital. And then also left behind without anything in it is this empty p orbital. Here color just represents sign of the wave function. So you have an empty p orbital on the same carbon as you have a filled sp2 orbital. So what that means is that the carbene is going to be nucleophilic in the sp2 orbital, but is going to be electrophilic in the p orbital. In other words, you have this double character to this carbon. It's both a nucleophile and an electrophile. And if you want to, you can think of the sp2 orbital as holding a negative charge and the p orbital as holding a positive charge. So this is a neutral molecule that acts like a carbanion and a carbocation at the same time. So that's kind of crazy because we've had carbanions, we've had carbocations, we've never had both at once. So this is something that can participate in reactions as both a nucleophile and an electrophile. Questions about carbene structure? Yeah. How stable is the carbene? It really depends on the identity of these groups. It turns out that just the regular old CH2 carbene is pretty unstable, and it's reactive enough that it's not that useful for the reactions we're going to be talking about. Lone pairs on the chloro group, groups stabilize this empty p orbital, and that lowers the energy of the carbene and makes it okay as an intermediate and makes it so that we can do these reactions. But in general, carbenes are more stable when the adjacent atoms have lone pairs on them. Okay, what else? Ooh, you don't want to know this, but I'm going to tell you anyway. Do you remember, probably not, do you remember in the pyruvate dehydrogenase complex how we used TPP ylid as a nucleophile? And we drew its structure like this. Vaguely familiar, right? We used that as a nucleophile when we wanted to do decarboxylation of alpha keto acids. Well, you can draw a resonance structure where, wait for it. No, seriously, wait. I don't know what I'm doing. you move the electrons from this carbon-nitrogen bond and put them back on the nitrogen. And then that carbon is no longer negatively charged. It's just neutral. So TPP ylide has a resonance structure in which it is a carbene. And when you go back and look, I mean, this is not important enough to memorize. If you go back and look at those mechanisms, you will see that the reason TPP is useful is because it is both nucleophilic and electrophilic on the same carbon. It has lone pair in an sp2 orbital, and it has something like an empty p orbital on the carbon. We sometimes call these heterocyclic carbenes because you've got a ring and you've got two heteroatoms attached to the carbene carbon. Anyway, you didn't want to know it. I told you anyway. Don't worry about it. That part's not on the test. You may need to use TPP ylide on the test, but you won't have to remember that it's a carbene. Okay, other questions? So let's do mechanism for these reactions shown above. We'll just start with the trans alkene. You just draw the carbon hovering over the alkene, and then you remember that the carbon is nucleophilic at the lone pair, but there's an empty p orbital on the carbon that can receive electrons. So the electrons from the lone pair electrons on carbon attack one of the carbons of the alkene, and then the pi bond of the alkene attacks the empty p orbital on carbon in the same concerted step, and that gives you the new three-membered ring. And there's no chance, because it's concerted, there's no time for rotation around carbon-carbon bonds, and so you get exclusively the trans stereochemistry. In a lot of ways, that mechanism should maybe look somewhat familiar to a mechanism that you would have learned about in 351. Sometimes people call this the butterfly mechanism. It's really kind of a stretch to call it that, but there you go. This oxygen is nucleophilic at its lone pairs. A lone pair can attack a carbon. Pi bond attacks the oxygen, breaks this weak oxygen-oxygen bond, and then there's some rearrangement to figure out where the proton ends up. But the idea is you have it in both cases, you have an atom that's both nucleophilic and electrophilic. And by the way, why do they call this a butterfly mechanism? Because if you turn it on its side and then suspend a huge amount of disbelief, then it sort of looks like a butterfly. Okay. All right, so that's cyclopropanation with a dihalocarbene, which is what we call this, which is what we call the carbene we used. Okay? So if you see a three-membered ring with two halides on the same carbon, you could, for example, use CHBr3 as starting material too. If you see that, be thinking, I could have made that from an alkene and from the corresponding dihalocarbene. Now, you're going to want to make three-membered rings sometimes that don't have two halogens on one of the atoms of the three-membered ring. But as I said, the CH2 carbene is too unstable to be useful, at least not in a cyclopropanation reaction. You tend to get rearranged products. So there's an alternative which allows you to use basically a CH2 carbene equivalent. You don't actually ever form the carbene, but the thing we're going to make reacts as though it were a carbene. And so this will allow us to make 3-membered rings with just a CH2 group. So the reaction conditions involve, as before, an alkene. And then we're going to use CH2I2, diiodomethane. And then we're going to use as another reagent that we'll consume. It's not a catalyst. We're going to use a mixture of zinc and copper. I don't actually know what this looks like, whether it's you grind up some zinc into dust and grind up some copper into dust and then mix them together and throw them together in the flask. I don't know whether you have to use a zinc-copper alloy and make bronze first and then do the reaction. And frankly, we're not even going to show what the role of copper is. So, but if you see this reagent, you'll need to know and memorize that it's going to do the reaction I'm about to show you. By the way, I promise not to give you a question where I'm asking you to fill in the appropriate reagent, and I do zinc, copper, zinc plus copper, all, wait, no, I wanted to do none of the above first. A and B, but not C on Thursday. And then F, all of the above. Right? I won't. Anyway, what I'm going to say is you're going to be able to recognize it easily. I'm very sorry. Thank you for indulging me. I was impressed this week with Come Follow Me study that there are dad jokes in the Old Testament. And the one that I found is maybe the first instance of the famous "Who's on first" joke, because when the Hebrews encounter manna, they use a word in Hebrew that just means sort of what, and so the sentence is, anyway, manna comes from a Hebrew word that basically says, "What is it?" or "It is what." And so you can imagine showing up and your dad gives you a bowl of manna and you say, "What is this, Dad?" And he says, "Yes." No, I'm trying to ask you, what is this? Yes, son, that is what it is. Anyway. So look for other dad jokes in the Old Testament. They're there. Another favorite is when Saul tells Samuel that he's performed the word of the Lord and he's supposed to have killed everything, and instead he's left the sheep alive, and Samuel says, "What meaneth then this bleating of sheep in my ears?" All right, sorry. I'm tired, you're tired, we're all tired. So let's show you, this makes a 3-membered ring, and you have the 2 CH2 groups, and you have the 2 protons on the CH2 group. Here are the 2 atoms involved in the alkene, and then here is the carbon that was present in our starting material. So the mechanism here is difficult. Well, it's not actually too bad, but we're going to talk about it. The reaction here is called the Simmons-Smith cyclopropanation. I'm not going to ask you which of the following is the Simmons-Smith cyclopropanation, but you may hear that at some point, and you'll know what they're referring to. So the first thing that's got to happen, if you're looking at this reagent, CH2I2, is we need to get one of the iodides to basically leave as a leaving group, and then we need to take the electrons in the carbon iodide bond and turn them into a nucleophile so that carbon can be both nucleophilic and electrophilic at the same carbon. Enter zinc. Zinc is a transition metal, let's see, and it's at the end of the transition series. By that point, we should have 12 electrons. So 2 for zinc would probably be in 4s orbitals, and then zinc would be a D10 metal, very electron rich. So it's easy for zinc to do the following. Electrons from zinc attack the carbon to make a new carbon-zinc bond, and then iodide leaves and makes a new bond with zinc. This is basically an oxidative addition step, because if you look at what we have after the reaction, zinc, which used to be at a 0 oxidation state, is now bonded to 2 X-type ligands. Oops. One of the iota groups is still on the carbon. So iodide is an X-type ligand, so is the carbon directly bonded to zinc. The complex is still neutral, so now this has to be zinc 2. All right? But notice what this has done for us. The X-type ligand is going to be kind of like a carbanion. This doesn't look so very different from a Grignard reagent or an organolithium reagent, right? So we can use the electrons in this carbon-zinc bond as a nucleophile. And then here, you've basically got on that same carbon an iodide leaving group. Now, the iodide's not going to leave on its own, but it could leave if the carbon is attacked. So we have a carbon that's electrophilic and nucleophilic on the same atom. All right, so that's the active reagent. If we take that zinc reagent now, and then we put the olefin here, we're going to show the electrons from the carbon-zinc bond attacking one of the carbons of the alkene, the pi bond of the alkene attacking the carbon, iodide leaving, and it's going to end up on the zinc. And that's going to give you your 3-membered ring with the atoms of the olefin still in the same stereochemical relationship to each other. They were trans to each other to begin with. Now they are trans to each other. And then the other byproduct is zinc diiodide. So in this process, we oxidize zinc from zinc 0 to zinc 2+. And we reduce the carbon because formerly the electrons in this carbon iodide bond belonged to iodide, but now they belong to carbon. All right, questions? Yeah?
So what was the purpose of using the zinc overall, the overall purpose of using zinc in this one and not in the
Why do we use zinc in this one and not before? Because this intermediate reacts like it was the carbene, but is stable enough to avoid undesired side reactions. Okay, what else? Okay, the what here is pretty straightforward. You can now do things like, well, the question is, could you do the synthesis? Could you plan a synthesis if I gave you this and said, what would the starting materials be? You'd need to recognize the structural pattern of a 3-membered ring with 2 halides on it. And then you could have made that from the dihalocarbene. And then you would have to pay attention to what the stereochemistry of the double bond was. Okay. And then someone actually during the 9 o'clock class asked, could you use this as a starting material? And then use like CH2 iodide and zinc, copper. And at that point, my evil nature got the best of me, and I said, good, Anakin, good. Because if you did that, you would, of course, make this lovely fused 6-membered ring with a 3-membered ring. I don't know how stable that is, but it was kind of fun and kind of evil looking. So I was very pleased. All right, I think that's enough on cyclopropanation. Why do we want to make cyclopropane rings? Well, you probably don't, but actually in the pharmaceutical industry, they tend to show up with some regularity in active compounds, and so it's nice to have the ability to make them in this way. All right, so final reaction of the semester is called olefin metathesis. Olefin is another word for alkene, but it's a little less nasal and so easier to say. It's a term from the oil industry. It refers to things that have pi bonds. So alkene metathesis, olefin metathesis. This is a Nobel Prize winning reaction a few years back. And we're going to use the catalyst that was invented by Professor Robert Grubbs at Caltech. And the what of this reaction is pretty easy. The how and why is a little bit more difficult, but we'll start with what. So we have these 2 monosubstituted olefins, and we're going to use a catalyst. I'm not going to tell you what the catalyst is yet. You're going to make the following 2 products. And this is why the reaction is called metathesis, because you basically break the 2 sigma and carbon bonds between those 2 sp2 hybridized atoms in the olefins. The terminal carbons are highlighted in yellow. The internal carbons are highlighted in purple. The 2 terminal carbons end up bonded together, and the 2 internal carbons end up bonded together through both sigma and pi bonds. So it's literally like a Lego reaction where you click the 2 parts apart here, you click the 2 parts apart here, and then you stitch them together. Okay. All right. A question you could ask is, your starting materials have 2 double bonds, your products have 2 double bonds, stability of products and starting materials is probably similar, which would make this reaction, you'd think, maybe in equilibrium. Why do we get the products shown here? And the reason we get the products shown here is because ethylene, you may not know this, but this is a gas. And so it removes itself from the equilibrium by bubbling out of the reaction mixture, and that drives us forward in this direction. Okay? And this is why, by the way, the starting material were these 2 terminal alkenes. The reaction works best if both of your alkenes that you're going to stitch together have a terminal CH2 group, because then you can make ethylene. Imagine the mess you would get if you had something like this, 2 alkenes, internal alkenes with each with 2 different R groups on them, you tried to do metathesis, you're going to get all the combinations of those 4 R groups on an alkene. So the reaction in metathesis, I'm just going to write here a mess. But then I feel somehow the need to illustrate how messy it would be. You get all those combinations. So the reaction is an equilibrium reaction, but the thing that saves you if you're smart about your starting materials is that one of the products is ethylene, and that drives you to the completion of the other product, right? This reaction can work in an intramolecular fashion. And when you hear me say intramolecular, and if you hate compounds with rings in them, that should strike fear into your heart, because yes, it will make a ring. Okay, so if we start with this alkene and we use the secret catalyst that I haven't shown you yet, we're going to, again, cut those 2 double bonds in half. The internal carbons are going to end up double bonded to each other, and the external carbons, the ones on the edge, the terminal ones, are going to end up as ethylene, which is going to bubble off. The 2 purple carbons are going to end up bonded to each other. So that part of our product is easy. The challenge then is drawing the right size ring. A classic error people make in these types of reactions is they forget that the terminal CH2 groups go away. So they look at that starting material, they count 8 carbons, and they draw me a stop sign with a double bond in it, which is pretty enough, but it's not the right product. Because remember, the 2 yellow carbons get clipped off and leave as ethylene. So if you start with 8 carbons, you end up with a 6-carbon product. And in this case, it's this 6-membered ring, and the double bond has to be cis. In general, you're going to get the most stable configuration of the double bond, but in the case of this 6-membered ring, the cis stereoisomer is more stable. You can't get a trans double bond in a 6-membered ring. And this is an example of what people have started to call ring closing metathesis. Okay. So, do you see the key issue? Do you see the pitfall you could avoid if you pay close attention to how this reaction works? Making rings is pretty useful, and it actually this is a reaction we've actually done in my lab. So in my lab, we're interested in peptides and proteins, and that's why I geeked out on dihedral angles and phi and psi values earlier. One of the long-standing goals of peptide and protein chemistry is to develop molecules that inhibit interactions between proteins. Some of these interactions between proteins are important for cancer and cell signaling. And the idea is if you could inhibit that interaction, maybe you could prevent a cancer cell from dividing indefinitely. So there's a protein-protein interaction in which 2 proteins bind to each other. A helix on one protein binds into a cleft on the other protein. And so people thought, okay, what if we just make a short peptide derived from that helical segment, and what if we use that to try to inhibit this interaction? And the answer was that it worked, but not that well for a few reasons. But one of them is that the helical sequence that was binding to this protein was anywhere between 10 and 15 amino acids. And those don't usually form helices very well. it turns out you need a little bit longer in general of a peptide to form an alpha helix. But that's when Professor Grubbs, who invented the catalyst we're going to talk about, and another professor at Harvard named Verdine, had this idea: what if we could, in a helix, as we showed you in the peptide chapter, the amino acids that are 3 and 4 residues apart. So if this is the I position, this would be I plus 3, this would be I plus 4, this would be I plus 7, are all on the same side of the helix. And so Grubbs and Verdine both asked this question independently: what if we used a ring-closing metathesis reaction to constrain these two amino acids that are supposed to be on the same side of the helix to be close together? If I force them to be close together, will the rest of the peptide form a helix? And so they made a side chain of various compositions. A lot of different things were tried. They made a side chain that had a terminal olefin, and then they exposed this to the catalyst. And and they anticipated that you could stitch the two purple atoms together, you'd make ethylene over here, and that the covalent constraint of those amino acids that were not close in sequence, but close in the final structure of the product, would hold the helix together. And they called this approach stapling, because a staple staples things together. I don't know, takes two pieces of paper and links them together. It's also probably because if you sort of look at it and imagine that line that represents the double bond sort of looks like a staple. In any case, this is an example of the idea of pre-organization, that if you link together two things that aren't really close to each other in the unfolded shape, but are in the folded shape, you make it much easier for that molecule to be helical. And there are now molecules in clinical trials for various cancers that are derived from this basic idea. All right, so that's a little aside about research. How much of that do you have to know? Only the stuff I said. No, you don't actually. It's not worth memorizing, but the idea of using this reaction to make a ring is important. All right. Let's talk mechanism. And this is kind of a pain. And I'm sorry about it. The mechanism involves a ruthenium catalyst. We're not going to worry about oxidation state here. This is the catalyst that was invented by Professor Grubbs. The other Nobel laureates, whose names are, I think, Professor Meldal and Professor Schrock, they have other catalysts, but this is the one that your text uses, and we'll stick with it. You've got two phosphine ligands. CY here represents a cyclohexane ring. So a cyclohexyl group, which would be like this, bonded to the phosphine. You have two chloroligands, and then you have this unusual ligand here, which is called an alkylidine. And in this case, a carbon that used to be involved in a carbon-carbon double bond is now involved in a carbon-ruthenium double bond. How did we get that? Don't worry about it. That's something that it's stable in a bottle indefinitely. You buy it from a chemical company. But this is going to be the catalyst that we use. All right? Now, that's generally not thought to be the active catalyst in the reaction. This is sort of a pre-catalyst. So I'm going to show you how we generate the active catalyst. If you look at this ruthenium complex, and again, I don't actually know how to count the d electrons here. I don't know if both of these bonds count as being with carbon, or if one is from the metal and the other's from carbon. So you don't need to worry about that. But this ruthenium right now is coordinatively saturated. There's no space for any other ligand. So first, we have to do a ligand dissociation reaction. And that's going to open up space for our alkene starting material to bind to the ruthenium. All right, so if we open up that space, I'm going to show one of the phosphine ligands leaving. Sorry about those thin lines. And then I'm going to show an olefin starting material coming in. And that olefin is going to interact as an L-type ligand with the ruthenium. Okay, so, and it's the pi electrons that are donating into that metal. All right, what's going to happen next is not an oxidative addition or a reductive elimination. It's not any of the reactions we've learned about. It's something new. People call this a 2+2 cycloaddition. What they mean by that is you're taking two atoms that are double bonded to each other, another two atoms that are double bonded to each other, and you're going to make two new sigma bonds. You're going to trade two pi bonds for two sigma bonds. So yeah, people will call that 2+2. You make a four-membered ring in which your original carbon that used to be on the ruthenium is here. Here are your two original carbons of the olefin that bound the ruthenium. Here's the other ligands. And then this 2+2 reaction is fast and reversible. So we can very easily go back to where we were previously by pushing arrows this way. That would just be the backward step. But if we push arrows this way, we make a new pi bond between purple and yellow atoms, and then we make a new pi bond between ruthenium, and we'll call this atom 1 and atom 2 of our alkene. So that step is often called a retro 2+2. And what that does is it releases from the metal a new alkene in which we've taken the purple carbon from the original pre-catalyst and bonded it to the internal carbon, carbon 2, on our olefin starting material. This is a byproduct that is not formed in very large amounts because you only need a small amount of catalyst. So if you're using like 0.001 mole% catalyst, you're not going to make very much of this at all relative to your starting material. Once we do that, though, we get to the active catalyst, which has a CH2 group bonded to the ruthenium. And this is now ready to coordinate another olefin. So this is now our active catalyst. Okay, questions so far about that process? Yeah?
So this process was just to get the catalyst to its active form?
This process was just to get the catalyst to its active form. You're going to see as the reaction proceeds, there's going to be a series of 2+2 and retro 2+2s to get the right things attached to the metal. Ultimately, where we're going to go is ultimately where we want to be is a place where you have a 4-membered ring with 2 of those R groups there, and then we can make our new bond, our new pi bond. Okay, other questions? Unfortunately, it's complicated, and I'm going to show you what happens, not necessarily tell you why it has to be that way. All right, so let's take our active catalyst now, and let's begin the catalytic cycle. We won't have enough time for all of it, but we can get a bit of a start. All right, here's your active catalyst. Again, we're going to have some of our olefin starting material bind the ruthenium as an L-type ligand. I'm going to remind you that this CH2 group came from atom 1 of our original olefin. Okay? And then here's our second equivalent of olefin, and I'm realizing now that the choice of purple was unfortunate. I don't know, maybe we'll go red. All right, so whoa. Okay, so we're going to do another 2+2 cycloaddition, just as we did above. Pi electrons from the olefin will attack the ruthenium. At the same time, we're going to break the ruthenium-carbon bond and make a new carbon-carbon bond. That again establishes this metallocycle. It's called a metallocycle because it's a 4-membered ring with a metal in it. And pay attention at each stage to the new bonds that we form. The key point here is we just formed a new bond between terminal carbons of our olefin. Okay, so that's where we're going to get ethylene from, because when we do the retro 2+2, man, this is ticking me off, you guys. I think I'm going to need to get a new Apple Pencil, which I think at this stage will involve a new iPad. So, yay me and goodbye money. All right, so that basically, at this stage, releases ethylene, and now we've got the purple carbon of our olefin directly bonded to ruthenium, and we've lost ethylene. Now, as I've said, these are equilibrium steps, so the loss of ethylene is an important part of this reaction because it's going to drive the reaction forward, because at each stage you can think, oh, I could go backwards. All right? So step by step, we are breaking apart the 2 carbons of our olefin. The terminal carbon is leaving as ethylene, and the internal carbon is now getting bonded to the metal. And hopefully you can see that if we bring in another olefin, we can do the same process, 2+2 and then retro 2+2, and we'll make a new bond between these 2 purple carbons. All right, I know that's a lot and I know we went through it kind of quickly, so we're going to pause there, and we'll pick that up on Wednesday.